Okay, so it's time for the first topics. The first topic is application in INRAE. The first speaker will be Roland Lenain. Roland Lenain is a research director at the French National Research Institute for Agriculture, Food and Environment, which is called INRAE, and heads the Lab for Robotics and Mobility for Environment in Agriculture, which is called ROMEA, in Clermont-Ferrand, France. His research activities are devoted to the autonomous navigation of off-road mobile robots, but also cover application in field and agricultural robotics. So he will present a talk about robotics in agriculture towards the adaptation of robots' behavior to meet new agroecological expectation.
Thank you so much.
You're welcome.
Hi, everybody. Yes, so my talk will be about robotics in agriculture, and most of this work has been done in collaboration with Institut Pascal in the framework of Laboratory of Excellence IMABES 3 and C-Site of Excellence CAP 2025. Sorry, I'm not used to cite it. Yes, we have been introduced this morning by Cyril about the interest of having robots in agriculture. I'll just take a few moments to go a little bit further because it's very critics today for having an agriculture which is environment friendly because it becomes more and more important to reduce the environmental impact of human activities. But in other hand, agriculture has to feed the world because there is a growing worldwide population, and we have to preserve the level of production in order to feed everybody. So we have to save the world in one end by reducing the pollution, and in the other hand by feeding everyone. In the meanwhile, we have also to reduce the risk for farmers when they are doing agricultural works because they are confronted to chemical products. And for instance, in Europe, one key point is the suppression of using chemicals, pesticide inside agriculture. And it's quite difficult for farmers because they have no today alternatives of using pesticide because the agriculture is less and less attractive because it's hard work, it's very painful, and then it becomes more and more difficult to hire people and to have manpower. And then in order to try to solve this paradox, there is some emerging agricultural practice such as precision agriculture to reduce the use of pesticides, so achieving the good work at the good time at the right place. It is also included into agroecology principle, which means to use the natural competition in between crops in order to limit the breeding, to limit also the arising of disease and so on. And we see some new kind of agriculture using urban agriculture and having some small farms all around the city. But the fact is that when you want to use this new practice, you need to go much more frequently in the field and achieve very accurate and very precise field operations. So due to the attraction of having robots, so mainly one of the main motivation nowadays is find manpower because of the hardness of the work. You have already some marketed devices, such as you can see on the screen. So Ecorobotics who propose a robot which is guided by GNSS. And it looks like on the ground with a camera, and it just detects the weeds and remove it using a very very small amount of pesticide. It reduces normally from 90% the use of pesticides. So this can be an alternative, but it's not directly organic farming. And you see, for instance, the Dino robots manufactured by NIO technology, who is achieving reading work. There is several versions with GPS, with camera. The idea is to change a little bit how the farm is organized because you have to go to the field very quickly because when you have a lot of weeds, you can do the difference between crops and bad plants. And there is also some concept of autonomous vineyard operation using the Bacchus robot, which is manufactured by Vitibot. So nowadays, if you have enough money. You can buy this one, and there is not so much, but let's say about 200-300 of these devices all around the world, actually in the farm. But the fact is that the capability of this machine is quite limited with respect to several big questions, several open questions that still arises in robotics in agriculture, such as how the agricultural practice moves with respect to the evolution of technology, how you can detect and adapt to the environment, how you are aware of what is the context of the task, how you adapt yourself to this context, and how you adapt the robots with respect to the task to be achieved. There is also a lot of question arises with respect to safety, not only scientific, but also legal questions. But what is required for a robot if we want to get him into the market? One of the main advantage of using robots in this area is that you don't use human. But if you need, for safety reasons, to have a human looking after the robot, there's not a lot of use. So we have to find together some technological step in order to allow the robots to move by themselves, comprising not only the field, but also in between the field, in the farm, and why not on the road. And one key point, which is more societal, is how we give human the capability to understand what the robot is doing and how we can work together between human and robots. And it's evident, it's clear for me that in agricultural applications, the robot would not be able to understand everything. And sometimes he has to detect by himself that he cannot understand the situation. And then he has to ask human what should he has to do. And then this question is quite important in order to let a robot go to the market and let the farmer use the robot in their everyday life. And so today, I will focus, I think, on what about developing and selecting the targeted behavior, which allows to do agricultural work in general and agroecological work in particular. So the fact is that when you consider a farm, you have the farm. I don't know if you see my, yes. Yes, you have the farm where the robot can be stocked and refilled and so on. You have to move on some fields, and fields can be of different states. You can have no crops at all, nothing at all. And when you want to do sowing, you have to be localized without any landmarks. You can have some vineyard, orchard. You have to go to this field, so you have some maybe road environment and maybe off-road environment, but still on a marked way. And there is also a big collection of conditions. You can have different kind of soil, different kind of terrain typology. It can be in slopes and so on, especially when you consider vineyard. You may have some big difference in the soil grip conditions. You can have a lot of change in the weather, and you have a lot of perturbations such as dust, such as changing lighting, and so on. And so the question is, can we do that by a single behavior? Of course not. And if you are okay, we will go a step further and consider some of elementary behaviors. So the first one, maybe the most important, because it covers a lot of, it can cover a lot of application, is the trajectory tracking. So let's say you have a trajectory, you can plan it. We had some talks this morning about task planning and task planning. And you want to follow it as close as possible, because the level of accuracy in agriculture is below 5 centimeters. So the ideal is some centimeters for the positions. And of course, it's much higher when you consider directly the work on the crops. And so if we applied some classical control law that you can find very easily in the literature, you have a lot of perturbations due to the bad wind conditions. And as you see on this kind of tests, it can change in real time because you are on concrete and asphalt, and then you will go maybe quickly on the grass. And this is not the same dynamics at all, and you have to take that into account. And then we have developed some new algorithm which permits to preserve the accuracy, whatever the grip conditions, which are based on adaptive control. So the idea is to estimate, not directly because you have no sensor which permits you to know what are the grip conditions. You have something like 10 parameters by tires which are changing due to the environment. And then looking at the difference between the expected evolution of the robots and the actual measured position of the robots, you are able to estimate some new parameters, some new variables, which are representative of the sliding, and then you can compensate for it. And another key point is the inertia of the vehicles and the settling times of the robots to reach a desired yaw rate. And then we have developed some predictive algorithms. You can have the details of this algorithm at the beginning in the Springer Handbooks of Robotics, and we have made an update in Encyclopedia of Robotics. Of course, this is the fundamentals, and we have several versions that you can find in the literatures. And one advantage of this kind of control is that you can apply this algorithm in different kind of robots at different speed and on different types of locomotion. For instance, we see here the RoboFast robot, which moves up to 10 meters per second, that is to say 36 kilometers per hour. And we see that even on complex trajectory, we are able to preserve the accuracy of plus or minus almost 10 centimeters if the trajectory is still achievable. This robot is 4-wheel steered, and we have also applied on unicycle. This is caster wheel in front of this robot, and you just control the difference of wheel speed between left and right. And we can apply it almost directly. You see also that it's quite different in terms of weight because it weighs 2 tons, and this one is only 500 kilograms. And we have recently applied it in some collaboration with startup on a Caterpillar robot with about the same accuracy. And so it's quite interesting because we have this first behavior allowing to control accurately a trajectory, whatever the kind of robot and the grip conditions. Now, another big application is to follow a structure using 2D LiDAR, or we will see after some extension. And so we work on these aspects by using an algorithm to extract the contour, the edge, using a point cloud. So we have a point cloud. We limit voluntarily the radius of the LiDAR. And using the deployment of circles, we throw a circle on the edge point. And at each contact point, we try to turn the circles and so on. And this permits to keep the points that are the closest from the robots. And then as soon as we have kept the point, we are able to define a trajectory. And we are able also to use the previous algorithm or to develop some new one using, for instance, backstepping control. The backstepping control is quite interesting in this case because it uses several steps. The first step is to find the desired, the optimal orientation at the given time to reach the trajectory. But when you do this step, you can also check that the orientation of the robot will not touch the structure you are trying to follow. So it's quite interesting because you have separately the control of the orientation and the desired orientation and the control of the yaw rate. And as soon as you have the optimal orientation, you can compute the yaw rate. So if you are in skid steering, it's directly the yaw rate. So you can deduce the steering angle if you are on two-wheel steering, and you can compute independently, if you have a four-wheel steering robot, the position and the orientations. And when you are in skid steering, one of the advantages is also that you can independently control the longitudinal speed if you have some difficult maneuvers to do. And this is precisely what we have tested there. First, it's interesting to work inside some building, because when the robot goes to the farm and goes to the refill station, he has also to use to move the inside buildings. And so we have made some tests, elementary tests in kind of building with different kind of obstacles, shams, and so on, to see the robustness of the approach. This is interesting because you automatically avoid obstacles as soon as the obstacle is at the level of the LiDAR. So here is the LiDAR. So this is a skid steer robot. And if I do it one more time, you will see that when you have very harsh curve, the robot will be able to decelerate, to brake, even to stop, in order to be as accurate as possible from at a distance from the shape. And this is the result. So we are plus or minus 10 centimeters. So the speed here is variables depending on the accuracy of the robot and the maneuver he has to do. So this was inside with a skid steer mobile robot. And now we can extend that to a four-wheel steering robot. I don't know if you can see very well on the video, but you may see better on the 3D representations that the wheel steering, the rear steering is moving in order to permit to have a good orientation of the tools we are using, which is a sprayer, with respect to the vegetation. So we extend in this works with a French insurance for farmers and the society Exact Robotics. We extend that to a 3D following, and then we find the good, the interesting points. And we have together a 3D reconstruction, such as you've seen this morning, of the profile of the crops, and this permits to activate one of the or all the sprayers, some sprayer, in order to limit the use of chemicals. It's interesting not only with respect to chemicals, because there is a lot of work nowadays that are proposed to develop biocontrol products. So it's products that are not so dangerous for the environment, but it's not so efficient. So instead of having 2 treatments per year, you have to do 1 treatment per month. So you have to spend much more time in the field. And so this kind of applications, having autonomous sprayer robots without using manpower and human time, permits to achieve quite accurate work without requiring time for people. So in order to extend it to 3D, we have also fewer following. So the idea now is to track the crops with in a top view in order to be more generic, because the robot is not always just at the level of the plants, of the crops, but usually it can go above the crops. So in this idea, the LiDAR is inclined, or we can directly use a 3D LiDAR. And in the framework of the LiDAR, we have a predefined shape that we expect. So it can be the wheel footprint, or it can be directly the crops. And as soon as we find this good correlation with the expected shape, we are able to have a relative position of the crops with respect to the robot. And using the robot motion by accumulation, we are able to define lines or curves to be followed, and we can use the same control as before. All I have talked about can be found in 2 articles that we published in Agri-Engineering this year. So it's quite recent. So do not hesitate to see this paper. And so this permits to have several many applications, and it permits to work with respect to the crops and not with respect to an absolute position, because the crops or the trees can grow up differently from the way we have sowed it. So it's important to have directly a reference with respect to the crops. And then you see on this unicycle robots of 2 tons that we are able to follow the vineyard with quite accurately without touching the ceps, which is very important for wine production. Second interesting thing is you can have directly the 3D representation, 3D reconstruction of the crops. And then you can start to make a little bit more interesting things, because you can also activate the implement, so the tools, in order to adapt yourself to the few centimeters you may have. So the algorithm is accurate within 5 centimeters. And then to gain the very last centimeters, you can activate the implement here, or you can use for weed removal operation for weeding. You can also use LIDAR, as we have seen this morning, or electrocution. I don't know if this is in English for that. So you let a current on the plant and it kills it. So one other interesting behavior for the development of robots is the cooperation, because one of the stakes is, instead of using very huge machines, you can use smaller robots and associate them with respect to the task to be done and with respect to the resources you need. And then instead of having big machines, you can use several small robots. And we have some association algorithms, so using here radio beacon, ultra-wideband beacons, which permits to have relative position and orientations. But so it permits for a robot to be a follower of one, but we can also extend that algorithm to mobile robot cooperation, even having a predefined trajectory. So we have worked in Journal of Field Robotics in 2017. Yes, we have developed a predictive approach which permits to avoid the propagation of error, and each of robot of a fleet is servoed with respect to the previous one, but also with respect to the one which is behind him. So it permits to anticipate for the modification of the speed, for instance, and then it permits to totally cancel the propagation of error. And so it has been tested with a very big machine, and we are testing it also with low cost and smaller machines, which are electrical vehicles. They are manufactured by Sabi Agri Society. And you see that we are able to have a very high level of accuracy, despite the fact that the trajectory is very curvy, and we are close to the maximal admissible steering angle. And we are able to have a lateral error, which is well in plus or minus 10 centimeters. And you see the entire distance within the robot. So you can see here on this video the longitudinal distance, and on the right videos, the lateral interdistance. And we are able to preserve this level of accuracy. And this permits to investigate several things. So adapting the number of robots to the task to be done, but it also permits to investigate the cooperation between human and robots, because in order to disseminate the use of the robotics, one can say, okay, I get one guy in a conventional tractor, and I have several robots which are following these guys. And I can have new big tools just with small machines. So now that we have several behavior, the fact is that we have to select with respect to the task to be done and with respect to the scenario. So what we have done for the moment is that we favored all the behaviors that are done with respect to the crops, and we have developed some metrics which permits to know if you have a good detection, if you are not so far from an expected trajectory or expected things. And using these criteria, this permits to switch from one behavior to the other, depending on the state of what happened. And then you see that we are following a trajectory. So in black, the black trajectory we want to follow. And in blue, this is the actual trajectory that has been achieved to the robot. And when we come here, so maybe after the curve, the robot will detect the crops, and it will switch from path to edge following, allowing to have a work with respect to the vegetation instead of that. So you see that it detects something with the LiDAR, but it is not in accordance with the trajectory. So it stays in path tracking mode. And as soon as we will find something which looks like not so far from the trajectory, looks like what he's expecting to find, it will switch naturally to edge following. And then it permits to work directly with respect to crops. So we just to wait 2 seconds. So right now, you will see he find a good path, and so he switched to edge. And after, if there is a difference with the trajectory, he switch back to path tracking. So you have almost the same. So I'm running out of time, not so much. I have 2 minutes remaining. You have the same with respect to the, it's 40, with respect to the furrow following. And what is interesting to do is also to do the adaptation of control parameters with respect to the state of the soil and the speed of the vehicle with respect to what you are doing. So we are developing also deep learning approaches, not to control directly the robot, but to adapt the parameters of PID control or horizon of prediction and so on. And you have some result of that in RAM. And so I came to the conclusion, since in order to develop agroecological principle and save the world, we need robotics. And we need robotics that are able to do accurate things. So we need several kinds of behavior, and we need also to go further in the direct work of robots with respect to the vegetation, and then develop new tools to directly act on soil and on crops. And so we have developed the behavior selection, not very simple for the moment. And now we have to go further with the environment recognition, such as we have seen this morning, in order to select the good behavior at the good moment. And also to detect obstacles, not only detecting, it's hard seen in off-road condition, because crops can be viewed as an obstacle, but it's not an obstacle, and then you have to discriminate them. And the idea is to use everything of that to develop a new concept for agriculture, allowing to apply concretely and for the farmers the concept of agroecology. I thank you for your attention, and a quick
Thank you, Roland.
question.
We are almost on schedule, so time for one quick question. Okay, come to the mic.
You know, there is a kind of geofencing or preliminary planning using Path Planner if you don't have the row, and if you have already the feed, there is a geofencing.
Okay, another question? I have one question. So on the whole, during your presentation, you didn't show anything about sloping ground and so this is always flat ground.
Yes, because it was not the topic of the paper, but yes, on the third, fourth, seventh slides, you add some of these aspects. Yeah. Up on the top one, the trajectory that is followed is on a mixed flat ground on the top of the hill. And the robot gets back on the middle of the rear and will goes in with a roll angle with respect to the slope. But it's true that this kind of algorithm are able to control the robot quite accurately on slope, even at high speed. We have made some experiments in this slope, at 7 meters per second, something like that.
Okay. What kind of task can be done at this velocity?
It's not necessarily agricultural task.
Okay. Okay. So thank you, Roland.
You're welcome. Thank you.